Assalamu alaikum. Welcome to the second lecture of chapter 6 on bulk deformation processes. Let us see what we will cover today. First, of course, we will quickly review what we covered in lecture 1. And today we will then continue with forging that we started last time. The major topic will be methods of analysis. Inside, we will talk of rectangular workpiece, cylindrical workpiece, the sticking condition, and die pressure, and this will take quite some time. Then we will start about flow stress under different conditions. We will work with several examples. We will talk of finite element analysis, the aspect ratio, and in the end of the topic, plane strain. After that, we will leave some topics of forging for you to study yourself, and that will hopefully complete today's lecture. So let us see what we did last. We introduced the field of bulk deformation. We gave you a big classification scheme of what different types of bulk deformation processes there are. We showed you forging, rolling, extrusion as some of the. Then we introduced again, right, what is bulk deformation, what is metal forming, what is a die, what is primary manufacturing, secondary manufacturing, general bulk deformation, sheet forming, classification of secondary processes, hot working, warm working, cold working, recrystallization temperature. Then hot working, what are the major factors, advantages, disadvantages. Cold working, what are the major factors and other. A very good chart sort of about the different processes of forging, rolling, extrusion, drawing, etc., and their general characteristics, how they are done, what is required, what type of products there is, and so forth. We then started with the one of the main bulk forming processes called forging. General introduction, how it is done schematically, the dies in two pieces. Then the classification of forging itself by equipment, by process, and some other common forging terminology. And these were the types of forging operations: open die, impression die, flashless. And then with open die forging, we were talking of normal forging and barreling. And then this is not directly related to this chapter. This is equations from material science, but which we will use in all the different operations. So engineering strain through strain, engineering strain rate through strain rate, force at any given time and height, and area due to constant volume, right? These are the equations which you know from earlier, but which we will be using quite often in this chapter. This was the last slide, grain flow in forging. And so there is where, therefore today we will start with where we stopped last time, grain flow. So if you can see here, right, if you can see lines, right, that the material is coming like this, going like this, coming like this. So there is a lower die, there is an upper die, there is a push from here, there is a push from here. So grain flow lines in upsetting means open die forging, right? A solid steel cylindrical specimen at elevated temperatures between two flat cool dies. So it means that this is hot, but the die here is slightly cooler, the die there is slightly cooler, and so on, right? So note the highly inhomogeneous deformation and barreling. Barreling you can see, right? Barreling you can see because here there is a sticking, upper there is a sticking. So when it is pushed outward, then it is pushed more in the middle, right? And the difference in shape of the bottom and top sections of the specimen. The latter results from the hottest specimen resting on the lower die before deformation proceeds, and so on. And here, if we had drawn these grid lines, and then we were doing upsetting or open die forging, then this will be pushed down, compressed, the width will increase and the height will decrease. And each of these squares will become these elongated rectangles. This will happen if there was very good lubrication and if there was no sticking between the die at the top and the material and the die at the bottom and the material. But if there was friction, then barreling will happen, and barreling means that this round shape, right, will happen. So, right, so you can actually do that. You can actually have a small piece of material which you cut into two pieces, and then on each face you make this grid line, and then you do the forging and so on, and after forging you see how it is happening, right? So that is what it is here. The original grid pattern, B after deformation without friction, and C after deformation with friction, right? So once we know exactly how the material is flowing through the process, then it's easier to do the calculations of forces and stresses and so on, and this is called grain flow. Now, the major thing, you are always interested in how to solve problems and how to do calculations. So methods of analysis, right? We could have started with anything, as I told you. We could have started with extrusion first and forging later, or whatever, rolling first, right? But the methods will be similar. So this is how to mathematically analyze a problem of bulk deformation. And the first method, which we will be using mostly, is called slab analysis of forging. Slab analysis. So here you see we are showing you the actual thing. There is the upper die in open die forging, there is the lower die, there is this material. This material could be a cylindrical round billet, or this could be a rectangular shape, right? We are assuming here that this is a block, a square or a rectangular block. In doing the analysis, we cut a small slab from it, right? This is, remember, this is a whole cube type of a structure, three-dimensional. And from there we are cutting a strip. So that strip which we cut out, this one, we cut this out. This is called a slab. This is normal English also, that from a large mass, if we cut out, we have butter, we cut out a slice of butter, we say it is a slab of butter. So because this is the method that rather than working on the whole volume, we consider only a portion of it. So we work only on a slab. So this is the slab method. So here you can study whatever, it does not matter, but the main thing is that whatever is the material, this is the center line, right? So your center line, because it will be symmetrical on the left and on the right, it will be symmetrical. So if you just do the analysis on one side, this will be enough. So the total width is A, if you can see from the center line. So the total material will be 2A in width. The height originally is H1. Originally the height is H1. And the X is in this direction from the center line. So if you take any small area, then this length is dx. From here to here is the distance x, and the thickness of this infinitesimal or a small slab is dx. So that is how you start with. Then if you take only this slab, right, which was placed at a distance x from the original axis, then this is the 2D view. This is the 2D view. This is the x-axis, so that is the y-axis, isn't it? So sigma y, up and down, sigma y. So a stress in the y direction is here. A stress in the x direction is here. If this was sigma x, then this is sigma x plus d sigma x. There is some small change. If this is sigma y, right, you know that if this is the normal force, then you multiply it by coefficient of friction and you get the friction force, isn't it? So if this is the normal stress sigma y here and there is a friction coefficient mu, then the friction on this side, the shear stress on the top, is mu sigma y. And of course, if it is there, then at the bottom also it is mu sigma y, isn't it? So this is very simple. There is nothing unbelievable about it. Very, very simple process. But if you do it, then you can get very good mathematical work done, isn't it? So once again, from the original place where you are measuring, this is at a distance x, and this is dx itself, and sigma x is in this direction, sigma y is in this direction. On this side, if it is sigma x, then on the other it is sigma x plus d sigma x, and because it is the normal stress on the top surface, then the shear stress is mu sigma y. This is a 2D view. Sometimes a two-dimensional analysis is enough and it gives us good results which are accurate enough. But if we need a full 3D, then this is the z direction, right? You know that this was the x direction, x, this was the y direction, so this of course is the z direction. And you know that it was sigma x and sigma x plus d sigma x and so forth. So this is sigma z, and sigma z they are averaging as sigma x plus sigma y by 2. Why they are doing it, we are not concerned with right now, right? But if we want to do a three-dimensional analysis, then this is the view of the slab that we will be looking at. And if we can do a two-dimensional analysis and convince ourselves that a 2D analysis would be good enough, then this will be good. So remember these things, right? Remember that this is the center, original width is A, and this is actually half width, and original height is h1, and this will keep on changing to h2, h3 and so on until it will become the final and so forth. Okay. So now on the previous page, if you look at it, then we are just asking you, don't read anything here, that if you go back to your statics, not even solid mechanics, statics, then how do you solve all the equations? What do you do in statics? If I ask you, this is just a digression, but if I ask you that describe the course of statics in very simple words to somebody who has not done it, what will you say? Right? So yes, if you are right, you will be surprised at your brief and correct answers. That the whole course of statics is about finding unknown forces and unknown moments in different situations, in normal loads, shear loads, rotational loads and so on, right? But so that is it. But how do you do it? What is the one basic principle? You apply equations of homogeneous, right? That is it. That isn't that what are the you just apply, you balance all the equations and you do it. So this is every time that these are some forces which are known, these are some forces which are unknown, and you apply the condition and then you are it. So here when you balance out the forces in the x direction, you see sigma x is the stress, multiply it by the height h, any height h, unknown height, right? Any height h. And the other dimension, if you take it as unity, remember, right? It is a face, h is the height, and there will be some depth. So in the depth, because you are not doing a 3D, in the depth take it equal to 1. So h into 1 is the area. So sigma x into h is the stress, isn't it? Similarly, d sigma x into h. So you are taking in the x direction, So these are the stresses. Similarly, mu sigma y is the friction stress. And dx is the thickness, and depth is 1. And this is at the top face and the bottom face, so you are doing it twice. And then sigma y itself is working on the h into 1 area. So very simply, you are not doing anything, you are just balancing out the forces in the x direction, and this is your equation.